The most varied media are filled into and drained via pipes from tanks every day. Examples are potable water, fruit juices, oils and fuels, acids or brines. Since these media can have completely different properties, there are different measuring principles to detect them. For example, level measurement according to the capacitance principle. The oldest capacitor design goes back to Ewald Georg von Kleist and Peter von Muschenbroek in 1745. In 1775, Alessandro Volta invented an improved capacitor which is regarded as the prototype of modern capacitors. In his honor, the SI unit for voltage is called volt. The discovery of electromagnetic induction by Michael Faraday facilitated the generation of electric fields which, together with the invention of capacitors, served as basis for applying capacitance instrumentation. In Faraday's honor, the SI unit for capacitance was called farad. Capacitance level instruments can be used for point level detection and continuous level measurement, particularly in liquids. The measuring principle is based on the change of the capacitance in a capacitor. Let's have a closer look at how this measurement method works using the example of continuous measurement. The space between two unevenly charged objects is called an electric field. In this space, one electric charge exerts force on another electric charge. The magnitude and direction of the electric field is depicted by field lines. If an alternating voltage is connected to a plate capacitor, current flows. The current depends on the dielectric medium between the plates, for example, air or media. A change of insulating material causes an increase of the dielectric constant and increases the capacitance of the capacitor and thus also the current flow. In addition, the current flow may be affected by the distance and size of the plates. These characteristics of a capacitor constitute the basis of the measuring principle of capacitive level measurement. The electrically conductive tank wall and a probe inside of the tank form a capacitor, the capacity changes of which are used to determine the level. In capacitance measurement, electrically conductive liquids and non-conductive liquids are differentiated. Measurements in conductive liquids, which are normally water-based liquids, are carried out as follows. The medium forms an electric short circuit from the tank wall to the probe insulation. Therefore, the measurement effect is only formed by the probe insulation capacitance gained from the media. This provides stable measurement which is independent of the tank geometry and the dielectric constant of the medium. If the level rises in the tank, the area of the capacitor increases proportionally. The measured capacitance change is used to determine the level. The capacitance change in non-conductive liquids, which are normally oils and solvents, is caused by higher dielectric constants of the medium in relation to air. The non-conductive medium forms an additional capacitor to the tank wall connected in series. It determines the total capacitance. If the level rises in the tank, the area of the capacitor increases proportionally. The measured capacitance change is used to determine the level, and increases as the level rises due to the higher dielectric constants of the medium. The measurement thus depends on dielectric constant of the medium and the tank geometry. Therefore, ground tube probes are predominantly used, which represent a defined geometry and additionally increase the measurement effect by small plate distances. In conductive media, conductivity greater than 100 microsiemens per centimeter, pre-calibration may be done at the factory because of the independence of the dielectric constant and tank, which facilitates fast commissioning. In non-conductive media, conductivity less than 1 microsiemens per centimeter, the respective dielectric medium must be calibrated at the customer's site. A small transition range between conductive and non-conductive media is referred to as the critical range. In this range, a minimal change in conductivity of the medium leads to a leap of the measured value. Applications in this conductivity range are thus to be avoided. Endress and Hauser instruments, according to the capacitance measuring principle, facilitate measurements of level interface, as well as point level in liquids and solids, even in applications with high temperatures or pressures, as well as in hazardous areas. We have a suitable solution for every application. Endress & Hauser.